All right, here's part two of the recording. Just got frozen out, but here we go. So we just talked about geometric series, and now we're talking about p-series. A p-series is an infinite series that is of the form where it's the summation as n goes from something to infinity of a constant over n to a power. So it's a constant over n to a power, okay? Now, if the power right here is less than 1, if this power is less than 1, then this series will diverge. But you guys probably can't see this. I think I did that, yeah. But if the power is greater than 1, then this series will converge. So for this example right here, the summation as n goes from 1 to infinity of 3 over n squared. So it doesn't matter what this constant is right there, right? It just has to be a constant. It can't be another, like, you know, e to the n over, no, that wouldn't work. But if it's a constant over n to a power, then that's a p-series. Because I have a constant over n to a power, and that power is greater than 1, this series will converge. But if this were 3 over n to the 1/2 or 3 over the square root of n, that would diverge. And even if we had it 3 over n to the first power, that also would diverge. So let me talk about that a little bit more, right? So let's look at the summation as n goes from 1 to infinity of 1 over n, okay? Let's look at these terms. Like, what does this look like? Well, that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, right? Now, a lot of people would think that this is going to converge because, hey, those terms are getting really, really small, and so that's going to converge to some value. It does not. This is known as the harmonic series, so that right there, which is equal to that. This is called the harmonic series. And it diverges. This diverges to infinity. All right, so that's what we got going on there. I usually go over a big, explanation about, why it, it converges, or a proof of, diverges, or a proof of why it diverges. But for now, just know this is known. It's a p-series where the p, or the power, is 1. That's known as a harmonic series, and that will diverge, okay? But then if you have any other series that is a p-series, such as, so this example, if I have a summation as n goes from 3 to infinity of 4 over n to the 1.00001. First of all, it doesn't matter what this constant is in the numerator, as long as it is a constant, divided by n to this power. So you have to ask yourself, is that power greater than 1? Well, yeah, it is. Because the power is greater than 1, that series will converge, right? That series will converge. So this guy converges. Now, we don't know what it converges to. We don't know that this goes to a certain value but all that we can say is that this will converge. If this, so now that converges. But if we had that this was 4 over n to the 0.99999, this guy diverges. That diverges, right? Because that power is now less than or equal to 1, right? So it's interesting that, you know, you have the sum of 4 over n to the 1.000000001 converges, yet 4 over n to the 0.999999999 diverges. But there's just that one value that is 1 for that power. 1 diverges and anything less than 1 diverges, but anything greater than 1, even if it's just very, very slightly greater than 1, that will still make that infinite series converge, right? And again, you could bring it back to, you know, like that story about me going to the stream with my brothers and how, you know, it looked like the pieces of, you know, the sticks were right next to each other and one went one way and one went the other. Well, it's like that, right? So we have where if that power is greater than 1, it's going to go in 1 and it's going to converge. But if that power is equal to 1 or less than 1, no matter how slightly less than 1 it is or how close it is to 1, it doesn't matter. If it's equal to 1 or less than 1, then that series will diverge. That's all you need to know about the P-series test. And the harmonic series is a P-series where P is equal to 1, okay? All right, so next we have the alternating series test. I messed with this just a little bit, so here, let me fix it really quickly. Okay, so this is the alternating series test. And again, this is from the paper that, you know, that series test worksheet that I gave you guys. And it says, if we have an alternating series, so all this means the -1 to the n minus 1, that n minus 1 is not important there. It could be -1 to the n, -1 to the n plus 1. It doesn't matter. As long as it alternates between positive and negative times a sub n. So right now they're calling a sub n the non-alternating part of each of the terms, right? And so if we have that infinite series alternates, and if, so the way that it's said is, if the n plus first term is less than or equal to the nth term, all that means is that those terms that aren't alternating, just the non-alternating parts of the terms, are decreasing in value or staying the same in value, okay? And if you take the limit as n approaches infinity of the non-alternating terms, and if that goes to 0, so if all 3 of those things are true, it alternates, the terms are getting smaller, and the limit of the terms goes to 0, then you have that series will converge by the alternating series test. Okay? I'll go through an example. I'll give you an example of that. So let's go to Rogowski. Are you guys still there with me? I haven't had any interaction with you guys, and I want to make sure that I'm not. All right, cool. Okay, here we go. So going to Rogowski, he has the, it's under 10.4 for alternating series. And let's go to this. He talks about absolute convergence versus conditional convergence. You don't need to know that. I still want you to know that, but I'm not going to talk about that right now. But let's talk about, that's no good. Let's go through some exercises. All right. Okay, let's look at number 3, right? I'm gonna take a picture of a bunch of these guys. Let's see these first 3. Okay, let's look at these. Okay, number 3. We look at that guy. Does it alternate? Yep, sure does. Next, the second thing is, so that's like the first thing that we need to check. The second thing, are the terms getting smaller? Well, and these are the non-alternating terms, right? So what is the non-alternating term? Well, let's call that a sub n. And that's just going to be 1 over n to the 1/3. Let's do that again. 1 over n to the 1/3 is the non-alternating part, right? Yeah, and by the way, we knew it alternated because of this -1 to the n minus 1. If it's -1 to the n, -1 to the n plus 1, -1 to the n minus 1, that just means that it's going to alternate, right? When we plug 1 in for n, this is -1 to the 0th power, so it's +1. When n is equal to 2, it's -1 to the 1st power, which is negative, and then positive, then negative. So that's what the alternating is all about. So now for this, the non-alternating part, as I plug in values in for n, starting at 1, then 2, then 3, then 4, do you agree that this right here is getting smaller? It's decreasing in values. When I plug 1 in for n, I get 1 over the cubed root of 1, which is 1. So that's 1. When I plug in 2 in for n, I get 1 over the cubed root of 2. When I plug in 3 in for n, it's 1 over the cubed root of 3. So here, I know that a sub n plus 1 will be less than or equal to a sub n, meaning that the terms, the non-alternating parts of the terms, are decreasing in value. That's correct, okay? And then the third thing that we look for is the limit as n approaches infinity of that non-alternating part. Does this go to 0? Does that thing go to 0? It sure does. So now, all 3 things that we needed for us to use the alternating series test to determine convergence hold true. It alternates, the terms are decreasing, the non-alternating parts of the terms are decreasing, and the limit as n approaches infinity of the non-alternating parts of the terms goes to 0. Therefore, I can say that this guy converges. So therefore, I would say this converges by the alternating series test. Okay? Now, when I look at this number 4, does that alternate? Yes, it does. Are the terms getting smaller? No, they're not. Because here I have n to the 4th over n cubed plus 1, right? So the numerator is increasing at a faster rate than the denominator. And so the second one isn't true. And the third one, if I were to take the limit as n approaches infinity of the non-alternating part, which is n to the 4th over n cubed plus 1, that goes to infinity. That doesn't go to 0. So therefore, this guy diverges. Okay? And then for number 5, does it alternate? Yes, it does. are the non-alternating terms getting smaller? Yes, they are, right? We have 1 over 1.1 to the n. So as n increases in value, that denominator is getting larger, which means that the whole thing is getting smaller, right? 1 over something that is increasing in value is decreasing in value. And so that is decreasing. And if I were to take the limit as n approaches infinity of 1 over 1.1 to the n, that does go to 0. So therefore, this will converge by the alternating series test. Okay? All right. Next, I wanted to, are there any cases where the test would be inconclusive? Not for alternating series test. But for the ratio test, which is where we're going next, there are, but not for the alternating series test. Okay, so, shoot, I'm gonna try to move this. So, all right. This is the ratio test. We've already talked about the ratio test specifically with, you know, the power series where there are variables in there. But this is the ratio test. And it just says, if you take the limit as n approaches infinity of the absolute value of the n plus first term divided by the nth term, if that is less than 1, then the series converges. And it's absolutely convergent, but we haven't talked about what that is. If that limit of that absolute value of the ratio of the n plus first term divided by the nth term is greater than 1, then the series will diverge. And if that limit of the absolute value of the ratio of the n plus first term divided by the nth term is equal to 1, then this is inconclusive. Look what I put down there. I said use this test if either the others aren't obvious or if what's inside the summation contains a mixture of factorials, geometric, and p-series. Okay, so let's go through a couple examples of how to use this. Oops, I don't want power series, I want ratio and root tests. Let's look for a good example for us here. Okay, prove that this guy converges. So here's what we're going to do. We're going to look at the limit as n approaches infinity of the absolute value of something over something. And here's what we do. The numerator is the n plus first term. So this is 2 to the n plus 1 over n plus 1 factorial. The denominator is just the nth term. So that's just 2 to the n over n factorial. Okay, so now we're going to look at this and we're going to say, well, this is just equal to the limit as n approaches infinity of the absolute value of 2 to the n plus 1 could be written as 2 times 2 to the n. N plus 1 factorial, if you remember, is just n plus 1 times n factorial. And then instead of dividing by that fraction, let's multiply by the reciprocal. So this is what we have. Now those 2 to the n's cancel out. The n factorials cancel out. And I now have that this is equal to the limit as n approaches infinity of the absolute value of 2 over n plus 1. Oops, that's it. Okay, so as n approaches infinity, what does that thing go to? Yep. It goes to 0, which is less than 1. So what did it say up here? Oh yeah, if the limit as n approaches infinity of the n plus first term over the nth term, the absolute value of that, is less than 1, then the series is absolutely convergent, which means that it's also just convergent. So I would say, therefore, this guy, this series, converges by the ratio test. Okay? All right. Let's see if there's one more good example. Let's just look at the next example. Example 2. So here we have, very quickly, the limit as n approaches infinity of the opposite value of, so this becomes n plus 1 squared over 2 to the n plus 1, which I'm going to call 2 times 2 to the n, divided by the nth term, or times the reciprocal of the nth term, right? And so now this ends up being, well, these guys cancel out right there. And this ends up being the limit as n approaches infinity of the opposite value. N plus 1 quantity squared is, n squared plus 2n plus 1 all over 2n squared. Okay, so because I have that the degrees are the same, and I'm taking the limit as n approaches infinity, this goes to the leading coefficient over the leading coefficient. So what is that limit equal to? One half. Good, which is less than 1. Therefore, this guy converges by the ratio test. Does that make sense? Okay. Now, here's what I want to say. So really, let's see. Did I go over everything I wanted to go over today? And then I have one other thing that I want to talk about. So let's see. Did we do? Yep, we did harmonic series and P series, alternating series tests, and ratio test. Okay, so here's what I just want to point out, okay? And this goes back to a little bit for the P series. There are 2 other tests that I usually teach that I'm not going to teach, but I just want to give you like an indication of what we got going on. So if I have the summation as n goes from 0 to infinity of, or let's make it 1, sorry, let's make n start at 1. N starts at 1. So let's make it n squared over 5n to the 4th plus 2n. Or first, let me not start with plus 2n. So just first this guy right here, okay? This is a basic P series problem. because what we have is, I could convert this into 1/5 divided by n to the second power. Do you see that? Because I have n squared over n to the fourth. So really the degree of the denominator is 4 and the degree of the numerator is 2. So really you could bring that, you know, n squared term and bring it down to the denominator and have it be n squared. And so then this, we know, converges by the p-series test because p is equal to 2, so p is going to be greater than 1, okay? However, this is something that I want to point out, okay? So then if we look at the summation as n goes from 1 to infinity of n squared over 5n to the fourth plus 2n, or something like that. So when we have like polynomials in the numerator and denominator, all you're looking for are the dominant terms of each of the polynomials. So when I look at this, what I would do is I would say, hey, let's, well, what could I use? Well, whatever, I'm just gonna do this. I'm gonna say, this guy right there is not the dominant term, right? 5n to the fourth is the dominant term of the denominator. The numerator only has one term, so that of course is the dominant term. So I'm looking at this as dominant term over dominant term, and that's just what I had up there. So it's gonna look like that, which we know converges, so this guy will also converge. I'm totally oversimplifying this, but basically what I'm saying is, if you have a dominant term, that's or I should say a polynomial over another polynomial, you look at the dominant term over the dominant term, and then that's what we base our decision on whether it converges or not. So this guy would converge. Even, so this converges. Really, that's because of some comparison test. I'm not teaching that, but even if I had, let's say the summation as n goes from 1 to infinity of n squared plus 3n minus 4 over 5n to the fourth plus 6n cubed minus 2n squared plus 1, whatever. I don't care. Dominant term, these guys you basically ignore, and this looks just like what I have up there, which I know converges. So I would say that this in the green, the whole thing that I had in the green, will converge. So that's just kind of a, as you're looking at some of these problems, it helps if you kind of use that as your guide and think about them as like dominant terms like that, okay? And it's not only polynomials, it's also roots. So it's anything to a power. So like the square root of n is n to the 1/2 power. So you could use it with the roots as well. Okay. I think that's all I want to talk about for today. Yeah, it's noon. Okay, so here's what I'm going to say. I put in my Google Classroom, there is an assignment that I put for you guys, and I have exactly what I'm going to collect next Friday. And then in addition to that, I also want you to be prepared to, over spring break to start the review, because really this is all that I needed to teach in terms of the new material. So that's it for AP Calculus BC that you need to know for the AP exam that you are going to take. I'm not really going to teach anything else that's new. From here on out, it's going to be a review, okay? Which is good. We still haven't heard from College Board on when the AP exam dates are going to be. But that's where we're at as of this point. We are done with the new material. I do have other problems that I want you to do. the first one that I have here, the 3 through 10, is what you guys had to do for today. And then the other 3 from Rogalski, the 2 through 4, these guys 2 through 4, that's what you guys are going to do by next Friday, and then turn those guys in along with the first one. And like I said, you take pictures and send that to me, and or submit that via this, right? And then I will grade those as they come in. Tomorrow from 9 to noon, I don't know if you guys need to have me. I will be here, but I'm really going to be compiling review stuff for you guys. But if you have any questions, I'll do that on an individual basis. And maybe I'll set up a Zoom meeting that I don't expect you guys all to be on, but I'll be here for, like, let's say from 9 to 10. If you have specific questions on the homework, whether the one that was due today, or if you work on some of these other ones that you want to see, I could set up a meeting, and I'll put that for you so you guys can all join on if you have questions. If you don't feel like you need to join. Okay. Any other questions for me? Sean, I was going to email you back about something. Oh, about your grade. Yeah. I'll email you. So P series is called harmonic only when P is exactly equal to 1. When P is equal to 1, that's the harmonic series. So it just has a special name. That's it. Just like Taylor series, when it's centered at 0 is called the Maclaurin series. The P series, when P is equal to 1, is the harmonic series. And yeah, the numerator, doesn't matter. So for example, if I had something like, the summation as n goes from 1 to infinity of 5 over n, you could think about this as 5 times the summation as n goes from 1 to infinity of 1 over n. So both of these are called the harmonic series because this power is 1, right? So yes, the harmonic series is just when the P is equal to 1. It doesn't matter what the coefficient is as long as the coefficient is a constant. All right. Anything else? Any other questions? Tyler, I like your video, but you're muted, so I can't hear you if you're saying anything. You just got an awesome background. Sweet. Can I get that? What do we got? Okay, all right. That's not my best face I've ever made in my life. But that's all right. All right. Cool. All right, guys. Have a good one. I will be here tomorrow if you need me, and I will post these videos to my website and to my YouTube channel. Have a nice day. Bye, guys.